Hey guys, welcome to another video. So in this video, I'll be talking about a limiting reactant as well as a molecular / empirical formula, what the differences are, and how to calculate them with the given data. So let's first talk about limiting reactant. Limiting reactant. So limiting reactant is it's essentially a reactant in a reaction that basically inhibits the progress of the reaction. So let's say reactant A has 3 moles, reactant B has 4 moles. When you use stoichiometry, you start with different points with these reactants. So you'll end up getting different amounts of products. But there's only one right answer, and the correct answer is with the limiting reactant as your starting point. So let's do an example problem. So we have sulfur dioxide plus oxygen yields sulfur trioxide. Before we do anything, of course, we have to balance this. So we get this. So let's say the problem asks you have 7 moles of this reactant and you have 2 moles of this reactant. How many moles of product do you get? Well, starting from each reactant, like I mentioned before, we'll get different moles of product, but there's only one answer. So let's take 2 cases. The first case, we have 7 moles of sulfur dioxide. Let's use the stoichiometric ratio. We get for every 2 moles of sulfur dioxide, 2 moles of sulfur trioxide. We get 2 moles trioxide. So we end up getting 7 moles of sulfur trioxide. So let's compare this to starting at this point. 2 moles of oxygen. Use the stoichiometric ratio again. So for every 1 mole of oxygen, 2 moles of sulfur trioxide. So we get 4 moles total of sulfur trioxide. So now let's compare the different starting points. The answer with the lowest number of final product is the answer. So the answer is actually 4 moles of sulfur trioxide. And with this information, the fact that 4 is less than 7, we know that this is the limiting reactant. So any problem where they give different amounts of reactant, we have to use this method in finding the limiting reactant and the correct amount of moles of product. But for instance, let's say there's a problem says, oh, you have 7 moles of sulfur dioxide, but oxygen is in excess. Then we don't have to do this do this whole process, because it's already saying that oxygen is in excess. This is our limiting reactant, so we have to start with this and do whatever we need to do. So now let's go into molecular versus empirical formulas. My bad. So let's talk about empirical formulas. Empirical formulas are whole number ratios of atoms in a compound. So for instance, water, carbon dioxide, stuff like that. We can't reduce this any further. If we reduce the 2, we get 1. If we divide 2 by 2 is 1, but 1 divided by 2 is 0.5, and that isn't a valid structure. It needs to be all integer values. So that's what empirical formulas are. Molecular formulas is something where, let's say, the number of atoms in this compound can be reduced. It gets reduced to CH2O. So that's essentially what a molecular formula is compared to an empirical formula. I'm going to do an example of how to find an empirical molecular formula. Let's do a problem right now. So let's say you have an unknown compound where you know that there are, it's 75.46% carbon, it's 4.43% hydrogen, and 20.10% of oxygen. And we know that the molar mass, based on the problem says that it's 318.31 grams per mole. So they're trying to ask us, what is the molecular formula? So we only have percents. We don't really know how many of carbon, hydrogen, and oxygen are in this molecular formula. But we know the percents and we know the molar mass. So what I'm going to do is a strategy where I assume that this compound is out of 100 grams. And that allows me to remove these percents. So let's say we have 100 grams. So we can say that for carbon, 0.7546 times 100 grams gives us 75.46 grams of carbon. We do the same here. We get 4.43 grams of hydrogen. Do the same for oxygen. Usually, I mean, you don't really have to write it out like this. You can probably do it in your head. But I just want to just show the thought process. And then once we start getting really practiced in this, it'll go by really fast. But we can't do anything with this. Let's use another color. We can't do anything with this unless we convert it to moles. And then we find the least common multiple and then find the ratios and get the molecular formula. So let's divide this by 12. We get 6.289 moles of carbon. Divide this by 1.008, we get about 4.39 moles of hydrogen. We do the same here, and then we get 1.256. So these are the ratio of moles that we have, assuming we have 100 grams of this unknown compound. So what we do now is find the lowest number of moles. So that's, in this case, oxygen, so with 1.256. And then we do 6.289, 4.39, 1.256 divided by this number. So we see here, let's say 6.289 divided by 1.256, get 5.007 moles of carbon. We do the same here for hydrogen. 4.39 divided by 1.256, get 3.5 of hydrogen. We do the same here for oxygen, of course. 1.256 divided by 1.256 equals 1. A mole of oxygen. Now, usually we can get the answer from this, 5, 3.5, and 1. That is the ratio of our formula, but we have to make this a whole number. So 3.5, what number can we multiply this to get a whole number? And that's 2. 3.5 times 2 equals 7. So we can't just multiply hydrogen by 2, we have to multiply everything by 2. So we get 10, 7, 2. So the actual formula is C10H7O2. But is this the answer? This is definitely the empirical formula because this is the simplest it can be. But let's double check with the molar mass that we have. We're going to find out actually that this isn't the case. This isn't actually the molecular formula because it doesn't correspond. It doesn't correspond with the actual molar mass that's given. So let's use black or something. So let's compare this. Let's find the molar mass of the formula that we got with the ratios that we got. So 12 times 10 plus 7 times 1 plus 16 times 2. We get approximately 159 grams per mole. But we notice something really interesting here. So the molar mass, 318 around 0.31, let's say. We divide it by the molar mass that we get from our formula, we get 2. So that all that tells us is that the formula, the formula that we have is nothing but a simpler formula, and we get 318.31. So essentially what we're saying is this is 159. By multiplying by 2, we get 318. And that's around what we have here. So now we know that the actual molecular formula is C20H14O4. That is our molecular formula, and that is the answer. Now obviously this process is really time consuming, really tedious, but once you get the hang of it, once you practice a lot more, the process becomes a lot faster. It kind of becomes second nature. So that's all for this video. Thanks so much for watching. As usual, check out my website that I made. It has a lot more material than just the stuff that I'm doing right now. Have a good day. See you next week.